Hello everyone, my name is Charlotte and I'll be your host for today. Welcome and thank you for taking part in this MDPI webinar entitled CO2 Valorization and Conversion into Value-Added Chemicals. This is the 8th webinar in this Catalyst series based on special issues from our journal of the same name. If you are interested in submitting any paper to any of the special issues that are linked to this webinar, please check the webinar's webpage. I would like to remind everyone that this webinar is being recorded and the recording will be made available as soon as possible on the webinar's webpage. Today's session is also being live streamed on MDPI's YouTube channel, so hello to those of you watching us on there. Certificates of attendance are available upon request. To get yours, please send an email to catalysts.webinar@mdpi.com. Certificates will be delivered to those of you who have registered and are watching on Zoom, not on YouTube. Thank you for your understanding. Today's webinar is chaired by Dr. Leonarda, Francesca, Liotta, and Dr. Giuseppe Bonura. Dr. Liotta is Director of Research at the CNR Institute for the Study of Nanostructured Materials and works in the team Materials and Technologies for Environmental Sustainability and Energy Efficiency. In 2013 and then in 2017, she gained qualification as a full professor in fundamentals of chemical science and inorganic systems. Dr. Liotta is ranking in the world's top 2% scientists. She is co-author of more than 200 articles or chapters published in international journals and books, and she contributed to more than 300 international and national conferences and informative works. Dr. Liotta has been invited professor at the University Claude Bernard, Lyon 1 in 2014 and 2018, invited professor at Lille University in 2016, and invited professor at Dunkirk University in France in 2019. She coordinates several international and national projects. She is responsible for the scientific part of the Memorandum of Understanding signed with Tomsk State University in Russia and with Northwestern Polytechnical University in China. And she is the scientific coordinator of PhD exchange program financed by the Chinese Scholarship Council. Dr. Liotta is also editor-in-chief of the section Catalytic Materials in MDPI's journal Catalyst and guest editors of several special issues. Dr. Bonura is a senior researcher at CNR Institute for Advanced Energy Technologies in Italy. In 2002, he graduated in industrial chemistry, and in 2009, he was awarded his PhD in chemical technologies and innovative processes at the University of Messina. In 2017, he gained the qualifications as an associate professor, both in industrial chemistry and in chemical and industrial plant and process. His main scientific interest concerns the field of heterogeneous catalysis, with main focus on the development of novel hybrid systems for chemical conversion of carbon dioxide into alternative fuels. In addition to numerous national and international conferences and seminars with several oral communication, he has already contributed to the production of over 270 scientific works, including more than 80 publications in international papers, several communication at national and international conferences, and various technical scientific reports related to contractual activities and the filing of one international patent. He is also editor of the RSC book, Sustainable Catalysis for Biorefineries, editorial board member of the journal Catalyst, and guest editor of the special issue Supported Materials for Catalytic Applications in the MDPI journal Materials. Thank you to both of you for chairing today's webinar. There will be 2 presentations today of 30 minutes each. The presentations will be followed by a Q&A session and discussion moderated by the chairs. If you have any questions for our speakers, please post them in the Q&A box at the bottom of your screen. Please remember to mention the name of the person to whom you're addressing your question. If you also want to take part in the discussion at the end, you can raise your virtual hand and I will hand you the microphone. That's it from me. I now hand over the microphone to our chairs and wish you a pleasant webinar.
Thank you, Charlotte, for your kind introduction. I'm Giuseppe Bonura. I would like to thank the conference team of MDPI for this opportunity to co-chair this webinar with Dr. Leonarda Francesca Liotta. I renew my welcome all the participants connected on the platform, and I wish the specific subject we are introducing can capture your attention. So if you like, there is space to post your question in the chat box of the platform. Well, as said, today we are going to discuss about a topic of great interest concerning the potential of CCU technologies according to different approaches on carbon dioxide valorization. These contributions are in line with the recent policies on CO2 recycling and utilization, because it's of great perspective using carbon dioxide as a feedstock for the production of bulk chemicals or fuels, so pushing the transitions towards a sustainable economy based on novel clean technological processes. So in a first lecture, Professor Nora Aishah Saidina Amin is going to deliver an overview on a promising approach for photoreduction of carbon dioxide into hydrogen using monolith-coated carbon-doped photocatalyst. Aishah Amin is currently Professor of Reaction Engineering and head of the Chemical Reaction Engineering Group at the School of Chemical and Energy Engineering of the University of Technology in Malaysia. Her specific know-how is in applied catalysis, reactor design, modeling, and reaction engineering. She holds 3 patents and 15 patent filings for her innovations. Her impressive scientific production includes 3 books, 6 book chapters, and more than 200 journal papers, with more than 11,000 citations. In recognition of her scholarly activities, she received the Top Research Scientist Malaysia Award in 2013 and 2018 by the Academy of Sciences Malaysia. She was also the winner of the Malaysia Research Star Award under the Outstanding Research on Global Warming and International Research Collaboration in 2017 and 2018. More recently, she was awarded as one of leaders in Innovation Fellowship by the Royal Academy of Engineering and received the Best of the Best award at INETEX 2020, being also a recipient of the PRGS 2.0 grant by the Ministry of Higher Education Malaysia. So before to give the word to Professor Amin, I would like to remember each speaker has 30 minutes for the lecture, while the space for open discussion is shifted at the end of the second lecture, introduced by Dr. Leonarda Francesca Liotta. Please, Professor Amin.
I would like to thank MDPI and the journal Catalyst for inviting me to give the talk entitled A Promising Approach for Photoreduction of CO2 into Hydrogen using Monolith-Coated Carbon-Doped Photocatalyst. So this is the outline of my research. I will start with a brief introduction, objectives, followed by methodology, results and discussion, and also conclusions. Okay, so the annual greenhouse gas emissions by sector actually comprise of mostly from the power stations, that is about 21.3%, and also industry process, about 16.8%. So this greenhouse gas, the composition of the greenhouse gas is made up of mostly carbon dioxide, which is about 72%, and about 18% methane, and the rest is nitrous oxide. So we know that excessive amount of greenhouse gas will give problems to climate change. For example, we will have severe droughts, severe flooding, and then we have such as like the devastating wildfires, and we have intense heat, and which is very, very bad for our environment. So there are several methods to reduce. Let me use this laser pointer. Okay, so there's there are many methods to reduce carbon dioxide. Among them is CO2 carbon capture, the thermal catalytic reduction, steam and dry reforming, and also plasma reaction. But the drawbacks of these processes are usually it's costly. So there is an alternative method where we can convert the carbon dioxide to several fuels using solar energy or using photo, and we call that photocatalytic system. So for example, we can take the carbon dioxide, okay, carbon dioxide coming from the industry, and then we can use a sacrificer agent, which means the carbon dioxide is reduced. And then we use photocatalyst, and we have a sacrificer agent or the reduction or the reducing agent such as H2O, methane, and then put it inside the photoreactor ultimately using the sunlight, and we can get different fuels, for example, hydrogen, methanol, ethanol, and methane. So in photocatalysis, okay, CO2 can be directly converted to syngas, chemicals, and fuels by the use of solar energy. So in this case, renewable fuels can be produced at low cost using sustainable systems. Okay, so we'll be looking at this photo technology of CO2 reduction using monolith reactor. And photocatalytic reactor use light as a source of energy, avoid the usage of chemical reagents. It occurs at ambient temperature and pressure, therefore it is a simplified process. Usually the photocatalyst that we use is titanium dioxide. It's a semiconductor. It has a large band gap, which is good for taking up the UV light. It is active in UV light, and also it is non-toxic, and it has a relatively high photocatalytic activity. However, there are some drawbacks of this TiO2. Remember that we have this photocatalytic reaction. That means we have a redox reaction, and that means the holes and the electrons need to be separated so that reaction can occur. However, TiO2 has fast rate of recombination. It is also low in crystallinity, and therefore the yield is low. So further modification is needed in order to increase the activity and yield. So for this work, what I'm going to talk about is we prepare the modified titanium dioxide. We modify it using glucose. So glucose, the advantage of using glucose is because it is abundantly available, and it is a part of the renewable material as well. Okay, so the idea is that we get this idea from the work that appeared in the Journal of Catalysis, where they actually reduce the chromium, okay, using the hydrogen peroxide. So they use the glucose, and they have this mechanism which we call the ligand metal charge transfer. And so we decided that to try this concept of doping glucose with the TiO2. Okay, so this is the glucose. What is glucose about? This is biodegradable polymetric structure. The good thing is it could act as a hole trapper and electron generator, and it is a suitable carbon source. So as mentioned before, that they have this mechanism, the ligand metal charge transfer, LMCT between TiO2 and glucose, and this will enhance the photo efficiency of the titanium dioxide. Okay, so we also know that for photocatalysts, we need to have a conductance band potential that is more negative than the H plus reduction potential. So if we look at the several materials, so TiO2 seems like a good candidate. Then this is the reduction or the redox reaction that will occur. We have H2O2 reduced to oxygen and 2H plus oxidation of water. And then that's where we get the reaction to produce from H2O to produce hydrogen. Okay, so that's how we got the idea of doping glucose with the TiO2. But from our also from our thermodynamic analysis, we also found out that there is other material, for example, like the G3N4, that have a narrower band gap and a higher conductance band compared to TiO2. So these are the NHE for the CO2 reductions. So we can see that if CO2 wants to produce produce HCOOH, so the voltage is about, the potential is about minus 0.61 volt, and for the formic acid is about minus 0.48 volt, and so on. So there is a possibility that when we reduce CO2, we can also produce methane and also methanol. So the reduction potentials of products should be lower than the conductance band. The reduction potential for hydrogen and methane minus 0.41 and minus 0.24, that is from the thermodynamics. So therefore, photocatalysts such as TiO2 and G3N4 with conductance band about minus 0.5 and minus 0.3 seems like a good candidate for us to try for the CO2 reduction. So the research gap is that only UV light catalysts have been investigated with low yield rates and product selectivity. So we need to compare the carbon dope, TiO2 and carbon dope, G3N4 using monolith reactor under solar light irradiation, and it has never been reported before. So there are several pathways, the reaction pathways of CO2 reduction with H2O to hydrogen has not been investigated in detail. So this is what we're going to do. We're going to look at in this presentation. So in this work, photocatalysts investigated are the carbon dope, TiO2 and carbon dope G3N4. Both photocatalysts are coated with monolith and tested for hydrogen production performance under the UV-vis light irradiation. Then we will take the best catalyst that perform, and we select that, and then we will elucidate the mechanism using the FT simulation. Okay, so this is the monolith photoreactor. So what are the advantages of having a monolith photoreactor? It says it has microchannel of different shapes and size. So this is the example of the monolith that we use in the lab. It is more efficient for light distribution over the catalyst surface. It has a larger surface area to reactor volume. And then because of there's a larger surface, so more illumination happens inside the channel, and larger conversion is reported with this photocatalytic monolith reactor. So we have here an example of the monolith with the G3N4 photocatalyst. Okay, so the experimental setup in the laboratory looks something like that. We have the reactor, we have the inlet streams that comprise of methane and CO2. And if we do the bioreforming, we will add water. And then we have the lamp, and also we have the solar panel. So this one is like the solar simulator. And the monolith is placed in the middle, in the center of the reactor chamber. And the products that we get is analyzed online using GC with TCD and FID. Okay, so our research objectives then is to synthesize and characterize carbon dope TiO2 and carbon dope GC3N4 nanomaterials coated with monolith. And after that, we want to investigate the performance of the photoreactor system for photo reduction of CO2 using the nanomaterials. And we want to simulate the mechanistic details of the photo conversion reaction to hydrogen. Okay, so how do we prepare the photocatalyst? Preparation of the CTiO2, okay, we start with the glucose and then we use the hydrothermal method, and also we calcine it according to these conditions. And after that, we will get the carbon, okay, glucose change to carbon. So then we just use that, it's a carbon dope TiO2. Similarly, for GC3N4, we also have the glucose, and then we heat it up, and then we can get the C, carbon dope GC3N4. This is the setup that we have in the lab. So the type of lamp is a solar simulator 91150 volt made by Newport. Light intensity about 20 microvolt per cm squared. And this is the and we use gas GC to analyze the product. And this is how we calculated the quantum yield. We have the number of moles, and then we have the electron, and also divided by the mole of photon flux. Right, now, when we want to elucidate the mechanism, we will use the DFT, theoretical DFT study. We will be using simulation software WEBS, VASP, by Kresser and Jobert. And then the basis is plane wave. Kinetic energy cutoff is about 450 electron volt. Axis functional is GGA plus PBE. The Van der Waals correction is the FT-D3 method. Well, the K-point sampling is we use the Monco's pack scheme, and the reaction path method is CI and AB code by Henkelmann. So this is the structure of the photocatalyst inside a 101 TiO2 plane surface. Okay, so let me continue now. We reach to the results and discussion. Okay, so when we tested the photocatalyst, so we have here just the carbon dope TiO2 and carbon dope GC3N4, and this is the monolith carbon TiO2 and monolith carbon GC3N4. So it is obvious that with the monolith, the performance or the photocatalytic activity increase. So for example here, it seems that the monolith carbon TiO2 gives the highest hydrogen yield as well as the highest methane yield. This reaction was conducted for 2 hours. So then we tested the stability of the photocatalyst, and we ran it for about 6 hours. So the stability of the photocatalyst is obvious that for monolith carbon TiO2 gives the highest performance. Okay, and then we also check the photocurrent testing of the photocatalyst for these monolith samples. And we can see that the photocatalyst also for the monolith carbon CTiO2, it gives a very good stability as well. So this is the characterization results. So we have here the DRUVVs. So for the C-dope TiO2 under the UV visible range, so C-dope TiO2, yes, it's under the UVVs, while for the C-dope GC3N4 is only in the visible region with the 400 to 440 nanometer wavelength. Therefore, the carbon dope TiO2 photocatalyst has larger harvesting light dispersion than the carbon dope G3N4 due to the use of solar light irradiation. So moving over, we have here the XRD results for the carbon dope TiO2 and carbon dope G3N4. So for the carbon dope TiO2, the crystallinity structure is obvious, while for the carbon dope G3N4, we have this amorphous structure. So from the photoactivity results obtained, crystallinity structure has better photostability compared to the amorphous structure. So from the BET surface, we have here the larger surface area for carbon dope TiO2. The pore size about 3.8 nanometer. For the G3N4 carbon dope, we have the surface area about 8 meters squared per gram and pore size is 7.9 meter. So the porosity of C-dope TiO2 is higher compared to C-dope, and this proves that the CO2 molecules could easily absorb on the active sites of the carbon dope TiO2. Next, we look at the FISM analysis over the monolith coated carbon TiO2. So here is the monolith surface without any photocatalyst, just the bare surface. This is the monolith surface with the carbon dope TiO2, and we have a different magnification. So it is obvious that for the monolith CTiO2, the nanorod TiO2 is obtained by coating on the monolith, and TiO2 sheets also was observed, inferring that TiO2 could have a better charge electron transfer, and also that from the EDX we can see the color mapping illustrates that the carbon on the photocatalyst is well dispersed. Okay, now this is the morphology of the carbon dope G3N4 monolith. And here we can see that for the monolith surface without the CG3N4, and then when we coat it with the CG3N4, we identify that there is a graphitic stacking layer on the monolith surface. So this is also good in terms of moving the electrons inside this for photo reduction. Okay, so for now we're looking at the theoretical DFT results. So we have here the model for CO2 adsorption, and we model it on the 101 plane surface of pristine CTiO2 and also C-dope TiO2. Okay, since the performance of carbon dope TiO2 is better, so that's why we want to find out the mechanism using the CTiO2. So for this work, we are focusing on the carbon doping at the bulk only. So the configuration of CO2 adsorbent on the pristine TiO2 and C-dope surface are based on the most stable configuration from previous studies. So CO2 adsorption on C-dope TiO2 surface has strong adsorption energy compared to the pristine TiO2 with the difference energy value about 4 millielectron voltage. So then this is the Ti, blue is Ti, O is the oxygen atom for the host, while the pink O is for adsorbate and C is for the carbon. Okay. So this shows the 4-step reaction process for the hydrogenation of CO2 reduction to hydrogen based on the possible formic pathway. So we have here top view and the side view for the first reaction, where we have the CO2 in the initial state, okay, plus the H, and we can then move over to the second step. So in this case, we have the intermediate HCOO star plus the H, And then we get that move to the third step. And we can see that in this third step, the initial state HCOOH star plus H, then is trying to form the final stage, that is the H2COOH. And then finally, in the fourth stage, we have this H2COOH, the intermediate, or the initial stage, forming the intermediate or the transition state, and then we get the hydrogen. Okay, so this is the side view for the third and the fourth step. Next, we will now go to the CIND results of formation of HCOO star and HCOOH star. So just now we were looking at just the whole reaction. Now we're looking at the individual reaction. For example, in reaction 1, okay, this is the energy barrier. And so for reaction 1 and also reaction 2, both are intermediate. The energy barrier for the first reaction is about 1.88 electron volt, while the energy barrier for the second step is about 0.5. So H position of the initial stage for reaction 1 and 2 are suggested to the bonded to O surface to form the targeted product. Okay, then we will go to the steps 3 and 4. We'll look at that. So in this case, we have the initial stage where we have the HCOOH star plus H. Then it's transforming to H2COOH star. So reaction 3 is an exothermic reaction with the binding energy about 0.19, with the energy barrier about 0.19 electron volt. Then in the fourth step, we have here the hydrogen, COOH star plus H. And then for the final stage, we can see that the hydrogen is formed and that we have the intermediate product HCOOH. So the energy barrier for the first step, for the fourth step is 0.72 electron volt. So in this case, the H position of the initial stage for reaction 3 and 4 are suggested to bond to the Ti surface to form the targeted product. Okay, so here we can see the full animation of the hydrogenation mechanism for CO2 reduction to hydrogen on the 101 surface plane of the carbon dope TiO2. So we can see that the hydrogen will be leaving the surface of the photocatalyst. So the overall favorable pathway that we get from this DFT simulation is as follows. We have the CO2 intermediate plus H to form a HCOO intermediate, and then followed by this COO intermediate plus H to form the formic acid, HCOOH intermediate, and then HCOOH intermediate plus H to form the H2COOH. And then we have finally H2COOH star plus H to form hydrogen plus HCOOH. So from there, we get all the information about the energy barrier, and when we add it up, so the effective energy barrier for this reaction is about 3.29 electron voltage. So in conclusions, from this work, we see that the carbon dope TiO2 and carbon dope GC3N4 photocatalysts are successfully synthesized via hydrothermal and polymerization techniques. Carbon dope TiO2 exhibits higher hydrogen yield compared to carbon dope GC3N4. So besides hydrogen, we also get methane, but for this DFT simulation, we only showing how to get the hydrogen first. Okay, the DR-UV-Vis results illustrate that the carbon dope TiO2 covered the UV-Vis region, which has high light harvesting from solar light irradiation, compared to just the carbon dope GC3N4, which covers visible region only. We also found from the simulation that the CO2 adsorption is more stable on the surface C-dope TiO2 compared to the pristine TiO2. So the overall pathway from adsorbed CO2 to hydrogen is proposed as follows, where the overall energy barrier is about 3.29 electron volt. So I would like to thank the Ministry of Higher Education for funding this project. And I also would like to thank my PhD student, Umi, whose work that I presented. And she just gave birth actually 2 days ago. So she was working hard, yeah, for getting the results for me to present today. So with that, I thank you very much.
Thank you, Professor Amin, for your very interesting talk. I kindly ask you to wait for the final session to reply some question. Now I pass chairing Dr. Liotta for next contribution.
Okay, so Giuseppe, thank you very much. Now it's my pleasure to introduce Professor Xin Tu. Professor Xin Tu is a chair of Plasma-Catalysis in the Department of Electrical Engineering and Electronics at the University of Liverpool. You received a PhD in physics from the University of Rouen in France and a PhD in thermal engineering from the University of Zhejiang in China in 2007. He was a postdoctoral fellow in the Center for Surface Chemistry and Catalysis at the Catholic University Leuven in Belgium from 2008 to 2009. Then, in September 2009, he joined the University of Manchester, working as a research associate in the School of Chemistry. He was appointed as a lecturer at the University of Liverpool in 2012 and was promoted to professor in 2019. He has been working for many years on the interdisciplinary research at the interface of plasma science and catalysis, directed towards environmental cleanup, fuel and chemical synthesis and nuclear decommissioning. Significant efforts have been devoted to plasma catalysis, where the combination of non-thermal plasma and heterogeneous catalysis has been used as a promising and emerging low-temperature process for the oxidation of gas pollutants in waste gas stream and conversion of carbon and nitrogen sources such as methane activation, CO2 conversion, nitrogen fixation, and biomass tar reforming. So please, Professor Xin Tu, is your floor with a talk with title Plasma-Catalysis, an emerging technology for CO2 conversion under mild conditions. Please.
Okay, thank you very much for the introduction. And also thank you very much for the invitation and to give me this opportunity to share our works on plasma catalysis. I'm Xin Tu, actually, from the Department of Electrical Engineering and Electronics at the University of Liverpool. And today I will focus on plasma catalysis, an emerging technology for CO2 conversion under mild conditions. And this is outline of my today's talk. So I will start with introduction about plasma catalysis. Then I will focus on 3 different reactions. One is plasma photocatalytic splitting of CO2 to CO. Then I will focus on plasma dry reforming of CO2 and CH4 into liquid fuels and chemicals. And then I will talk about CO2 hydrogenation to methanol. So the motivation of this work actually is driven by the current, global energy challenges. So we know that the increasing energy demand and also pressure of supply due to the depletion of fossil fuels. But at the same time, you will see that, for example, the UK emits 470 million tons of CO2 per year. So this actually that cause greenhouse gas effect and also global warming. So there are different ways for CO2 conversion and utilization. For example, this is chemical transformation approaches. So for example, the science and the technology roadmap on catalysis for Europe, has highlighted that it has, the chemical transformation of CO2 into useful feedstock chemicals and fuels will become a key element of sustainable low carbon economy in the future. So I had just summarized the different chemical transformation route actually for CO2 conversion. For example, CO2 decomposition to CO and oxygen. Of course, this process could be very difficult for thermal catalysis. Of course, it's possible for like photocatalysis or electrocatalysis. CO2 hydrogenation, CO2 reduction with water to produce syngas is also possible, but it's also very challenging. CO2 hydrogenation has attracted increasing interest to produce, for example, CO, CH4, or like liquid fuels like methanol. Another very promising process is stratiforming of CO2 and CH4 to produce generate syngas, but also like olefins and oxygenators. So I just want to give you some brief introduction about plasma, because maybe some of you do not know much about plasma. So plasma was first discovered by Longmill in 1928. Okay, so you probably know that plasma TV in principle is similar. Plasma actually is an ionized gas, ionized gas. So a distinct fourth state of matter, different to like a solid, liquid, and a gas. So plasma actually, is a mixture of energetic electrons, ions, free radicals, excited species, neutrons, and also photons. So plasma contain this different, active species which can involve in different chemical reactions, can easily break the, chemical bond. So you can see the different plasma systems. For example, this is a typical, dielectric battery discharge, and this is the dielectric battery discharge packed with, barium titanium oxide, and this is gliding arc, and this is rotating gliding arc. So this slide will show the major advantages of no thermal plasma, or we call cold plasma. From this word, actually, you can see that the major advantage of plasma process is low temperature, and the temperature can be as low as room temperature. And the plasma can generate a range of highly energetic electrons and chemically reactive species, free radicals, excited atoms, molecules, and ions to activate chemical bonds to initiate, chemical reactions. The plasma reaction is faster, it's instant. You can switch on, switch off plasma system instantly. So this offers the flexibility to be combined with the current like renewable energy sources, for example, like variables or intermittent power for energy storage. And the plasma process can enable thermodynamically unfavorable reaction to proceed. For example, dry reforming usually requires very high temperature. The plasma system can be small and it can be large. It's also flexible to combine with other technologies such as catalysis. So the major advantage of plasma catalysis actually is the first one is synergistic effect resulting from the interaction between plasma and the catalyst surface, for example. Plasma can reduce, metal particle size and enhance metal dispersion. This has been used for the catalyst synthesis or catalyst surface modifications. For other, catalytic process, for example, thermocatalysis or like photocatalysis or electrocatalysis. So the plasma catalysis actually can improve the selectivity, yield, and energy efficiency of the overall process. Also minimize the formation of unwanted byproducts, for example, like NOx or for VOC removal. So I just want to go through the different configurations of plasma catalysis. So how you can combine plasma with catalyst. Okay, the one very common one is we call single state systems, or in plasma catalysis, you can place catalyst into the plasma. So you can imagine that the interaction between the plasma species with the surface. So all the plasma generated species can directly interact with the the catalyst surface or even, pores of the catalyst. So this is more complicated, but this is also very common for plasma catalysis. So you can work on this kind of reactions at low temperatures. And the other option is two-stage systems. So you can put catalysts, in before plasma or after plasma. So we often put this after plasma. We call this is post-plasma catalysis. So this is more like a plasma process plus thermal catalysis. But of course, you can heat it or not heat it depending on the process. So this is often used for example, like a VOC destructions. You might need a catalyst to remove ozone. In my actually the works, and we will just focus on the in plasma catalysis. So we put catalysts in the plasma systems. So plasma catalysis is a very complex process. And you can imagine plasma is already complicated and catalysis is also complicated. So there's interaction between the plasma and the catalyst. So we generate different effects, for example, packed bed effect or enhancement of plasma generations. And also you can have some absorptions directly from the plasma generated species. And also the plasma can also affect the catalyst properties. Because plasma can generate, excited species which do not exist in like thermal catalysis, and also can improve the metal dispersion and reduce metal particle size. And in terms of the reaction mechanism, it's really complicated, because here you see the plasma surface intentions, and it's not just the LH, mechanisms or route, and also involves ER route. Any species directly from the gas phase can also be absorbed onto the surface directly, and also there's others, reactions. Okay, now we start with the first reactions, plasma photocatalytic CO2 splitting. So we use a typical, we call dielectrical battery charge reactors. You see this is plasma generated in between, two electrodes. So this is the core tube, and you have electrode inside, and you have another electrode outside, and between them you get plasma. And we put catalyst alongside, the bottom of the reactor. And this is the conditions. We just use a pure CO2, and we use two materials. One is titanium oxide, and the other one is BaTiO3 and barium titanium oxide. Here you can see the results. Without any catalyst, just the plasma only, you can get about like 16% conversion. But when we use a catalyst, we can enhance the conversion to about 38%. So significant enhancement can be observed. And the temperature is only 150 degrees. So if you just use 150 degrees without any plasma, you get nothing. So clearly, we can see that clear, synergistic effect of plasma-catalysis, which means the plasma plus catalysis is better than the sum of plasma alone and the catalysis alone. So we have tried to understand why this happens. For example, we know plasma can generate UV, so we measure the UV intensity generated by plasma, which is quite low compared to that, the conventional, UV intensities used for like photocatalysis. And also we measure the temperatures. You can see the temperatures increase with the time and almost constant. After about 25 minutes, it's about 150 degrees. So the temperature is really low. The UV intensity is also low. And we believe the synergy effect of plasma catalysis is induced by two effects. One is a physical effect, which is due to the change of electric field due to the partial packed bed effect, because we put catalyst in the plasma, which can affect the electric field, which affect the chemical reactions. On the other hand, I think the most important is the catalytic effect, photocatalytic effect. For example, the formation of electron hole pairs, and also the formation of oxygen vacuums. So there's two mechanisms which can induce, photocatalytic reactions. One is from the UV, from plasma. And we believe this is quite minor. It's very minor because the UV intensity is really low. The other, that because in plasma, we can get highly energetic electrons. For example, the electron energy can larger than like 3.2 eV or larger than 3 eV, which can activate photocatalyst to produce electron and hole pairs. So we feel this is the major contributions to the enhancement of the conversion. And then we have done the experiment, and we see the formation of like a Ti3 plus, which demonstrates the formation of oxygen vacants on the catalyst surface. And also we find more Ti3 plus species in the BaTiO3 compared to titanic oxide. So this actually demonstrated that this is possible route for the photocatalysis directed from plasma. And here you can see that we have show the conversions and energy efficiency for this process. There's a clear trade-off. When you have higher conversions, you normally have lower energy efficiency, but when you have lower conversions and you have higher efficiency. However, if we use catalyst, we actually can to actually break this trade-off. And you can see here that this work actually is 11th, which is give a reasonable higher, conversions, but with relatively high, the energy efficiency. The next work I will talk is CO2 dry reforming of meeting and CO2 liquid in one step at room temperature and ambient pressure. Okay, so we know that normally if we want to produce liquid field from CO2 and CH4, we need to go through two steps: one high temperature process, and the other one is high pressure process. Okay, it's from syngas route. If we want to go directly from CO2 and CH4, this is really difficult due to the thermodynamic barrier. However, we can use plasma-catalysis to achieve this one in one step, direct route and at ambient temperature and ambient pressure. So this process is quite promising, for example, for like biogas, conversion to liquid fuels chemicals directly. So because the liquid chemicals can be easily transported. So you can see this is one plasma reactors, and different to the previous one is that this reactor had water cooling. So we use water as electrode and also use water for cooling the reactor, so we can keep the temperature, at room temperature, and we change the different parameters. For example, we fix the power is like 10 watt, and we can change the ratio of CH4 and CO2, and we use different catalysts. Please note that we use argon plasma for the calcination of this catalyst. We do not need to use any like hydrogen, because this is like plasma can generate electrons, which can also reduce the catalyst. So here you can see the results without any catalyst. Okay, so only using plasma, we can also produce liquid chemicals. So you'll see that when we change the ratio of CH4 and the CO2, and we see the change of the selectivity of the four liquid chemicals, we see that 1,1 actually you get the maximum acetic acid. The acetic acid actually is the major product. It shows the 100% atom economy, because it's just one molecule of CO2 and one molecule of CH4. And you will see the methanol and the ethanol, they are competing actually. The methanol actually increase and the ethanol decrease, because they all need CH3 radicals. Acetone is, the selectivity is very low. So we have measured the optical emission spectroscopy to see which kind of species are formed. So you can see that we have detected like CH, CO2, CO, CH. And if you look at the intensity of this species, you will see that the CH, decrease when you increase the CH4 CO2 ratio, because when you have more CH4, you get more CH hydrogen and also C2 species. And if you have higher CO2, you get more CO and oxygen. And this is the major results with the different catalysts. And we can see that the COP catalyst show the best selectivity for the acetic acid. And if we use formaldehyde, if we use noble catalyst, we can also produce formaldehyde. You will see that platinum and gold. But if we use just the support only, we can see that it's only, decrease the product. The selectivity of liquid products. Okay, and this is the proposed mechanisms or reaction pathways to form the methanol and acetic acid and ethanol. You will see that CH3 with OH can produce methanol, and also CO with CH3 can also produce CH3CO, and with and then it's reacted with OH to produce acetic acid. And here you can see that CH is very important radicals, because it's competing for the production of methanol and ethanol. And the last part, we will talk about CO2 hydrogenation. So similarly, you'll see that conventional you requires high temperature and high pressure to make this reaction happen from CO2 hydrogenation to methanol. However, we can also use plasma to get methanol at room temperature and ambient pressure. We use 3 different plasma systems. Here, we actually make some small modification of the reactors. The reactor 3 is the one that, same as the previous reaction. Okay, it's water-cooled reactors. And the middle one actually is also water-cooled, but we use double dielectrical for the inner electrode. Okay, and the first one, the reactor 1, is no cooling. So the no cooling, the temperature is a little bit high, it's about 300 degrees, okay? For the cooling is only 30 degrees. And you will see clearly that without the cooling, actually the temperature is higher. So the major product is CO, not methanol. But when you use water-cooled reactors, you'll see the major products is methanol and also ethanol. And we also test the different catalysts. You can see use platinum and also copper catalysts can increase the methanol yield. Although the selectivity is not changed significantly, it's almost same. And in terms of productivity, the energy efficiencies, and we currently is only 0.05, but we can increase this one when we use a nickel cobalt catalyst, increase 3 times. And for the same reactions, we have also tested cobalt oxide catalyst supporting on manganese oxide. Okay, we use slightly different reactors, but we use similar conditions like H2 and CO2 is 3 to 1, and also room temperature. And here you can see the 15% loading of cobalt oxide actually show the best conversion and also the selectivity of methanol. We get to the methanol yield is 10%, and then we change the different loadings and we try to understand what happens. Okay, we also have tried just cobalt oxide and also the support only, and you will see this cobalt oxide does not produce a reasonable higher CO2 conversion. And first, we have done the electrical diagnostics to understand how this material changes the plasma properties. And we can see that there are some changes when you use the different materials. For example, cobalt oxide supporting on MgO and also plasma only, they're different. So they change the plasma properties. And also, we find that the cobalt loading actually does not change electrical signals, which means the cobalt loading does not affect the plasma properties. Okay, so the different the performance when we use different cobalt loadings, it depends on the catalytic effect. So we have done the different catalyst characterizations. For example, the XRD, and which shows it's major like MgO, peaks, and the catalyst before and after reactions are almost same. And we see the BT surface area is slightly lower for the higher loadings. And the TM shows actually before and after reactions, the cobalt oxide and nickel nanoparticles, are almost same. But here we find that the higher metal loading is actually leading to the large particle size, and it could be much more difficult to be reduced, during the reactions. You can see that the partial reduction of cobalt 304 to cobalt oxide during the reaction, because it's in a plasma and also with the presence of hydrogen. And we also find that the surface, cobalt 304 and the cobalt oxide interface could be the major, active centers for the reactions. The stability is over 4.5 hours seems is okay, slightly decreased due to the deactivation. And this is proposed reaction mechanisms as many on the surface. So in plasma catalysis, normally in addition to the gas phase reactions, there are also some surface reactions. But in this CO2 hydrogenations, the CO produced from plasma process or the gas phase can be directly absorbed onto the surface. So there's also existence, presence of the CO hydrogenation route. So this is CO hydrogenation, and this is CO2 hydrogenation. Through one is reverse water gas shift reactions followed by the CO hydrogenation or the the formate pathways. Okay, so this is just a brief summary of my talk. So you can see that the plasma can generate highly energetic electrons, which can activate photocatalyst, and not just for CO2 splitting, maybe could be for other plasma chemical reactions. And we find actually the plasma generated UV actually does not make a significant contribution to the activation of photocatalyst. And we have demonstrated the direct conversion of CO2 with hydrogen or CH4 into liquid fuels and chemicals in a single step process at ambient pressure and ambient temperature. And we actually found that the major product is acetic acid, but also methanol, ethanol. And formaldehyde can be only produced when we use noble catalyst. For CO2 hydrogenation, the major product is methanol. You can see that reactor structure is quite important because it can change the plasma properties and also the temperatures, which affect reactions and produce different chemicals, for example, CO or CH4 or methanol. So more catalysts needed to be tested and to further improve the conversion and also selectivity of target chemicals. This is the Plasma-Catalysis roadmap actually we developed last year and we published in Journal of Physics D. So a group of 16 scientists actually contributing to the different parts of this roadmap, and we cover different sections like different chemical reactions, also the modeling and diagnostics. So if you're interested, you can have a look at this paper. And this is acknowledgement of our colleagues and those students, postdocs, contribute to this work. And also, we also appreciate the financial support from EPSRC and also Horizon 2020. Thank you very much. We also have postdoc positions and also studentships in these areas.
Okay, so Professor Xin Tu, thank you very much for a very interesting talk. And now we have time for discussion, and I would like to invite people who are attending the webinar if they have some question directly to put in the box. And I see that there are at the moment 2 questions, and I would like to start to read. So the first one is quite general, is about the latest updates on CO2 valorization and conversion into fuels, and what is the way forward and how a rational design of catalyst can be routed. So probably this one is related to the first talk. I would like to invite Professor Saidina to reply, please.
Yeah, about this CO2 conversion, what is the way forward? Okay, we know that CO2 is a stable molecule, and it is not easy to convert CO2. So we need something like, if we use thermal, we need a very high energy. So plasma, photo, and then we also have photoelectro photoelectro, and then maybe we have microwave plasma. So probably those with high energy, but clean energy, that can be used for converting the CO2. And does that answer your question?
Yeah, the question is just about if you wanted to suggest a rational design of a new catalyst eventually.
Right, thank you.
Okay, perfect. So I continue with the second question is for Professor Xin Tu, and the question is related to other route for CO2 conversion, like electrochemical route, can also be carried out at room temperature. What would you consider as the key advantages and disadvantages of plasma catalytic conversion of CO2 compared to electroreduction of CO2?
Okay, thank you very much for the question. Yeah, I mean, first I would say I do not know much about electrocatalysis. But my understanding that electrocatalytic CO2 reduction to like fuse chemicals, for example, like methanol or ethanol, has some issues with like too many like products can be produced, so the selectivity might be an issue. The other, I think the other challenges could be that I'm not sure about the scalabilities, but if I look at plasma catalysis, it's more like thermal catalysis. All the reaction pathways is very similar to thermal catalysis. Of course, plasma catalysis will introduce gas phase reactions alongside the surface reactions. But I think I would say like both process could be very promising, you know, because in terms like the localized or distributed, you know, energy storage using renewable energy sources, because both use electricity. But I think perhaps both process still has a long way to go for like the full commercializations, but still need to do quite a lot of work in these areas.
Okay, thank you. And Professor Tu, another question for you is just related to the use of plasma. The question is related to there is a local increase of temperature when the plasma is used.
Yeah, the temperature of the plasma actually can be controlled by, you know, a range of parameters. For example, power is I think the major parameter which can control the plasma, and also the power supply. For example, if you use pulsed power, and you can get lower, you know, the temperature. And so in our case, I mean, we use water cooling to control the temperature. This is like forced cooling, so we can also control the temperature to very low, and or slightly higher depending on the, you know, the cooler, because we can set the temperature in my cooler and to control the temperature. But if you do not use like cooling systems, you can still control the temperature by control your parameters like power, frequency, you know, flow rate. So yeah.
Yeah. Okay. So I would like to continue with the following question. This is for Professor Nor Aishah. The question is about the effect of the monolith on the catalytic activity. Does the material of the monolith influence in the catalytic activity?
Right, so thank you, Vicente, for that question. Okay, of course, if we look at the materials, okay, material-wise, so it probably will interfere with the result. So when we choose the material for the monolith, we want to choose inert material. And then when we coat it, we want to make sure that it is uniformly coated, so that when the light irradiates onto the photocatalyst, only that actually react. So we have to make sure that our monolith is inert and it does not react. So that's a very important study, or very important initial study that we have to make, so that our material for the monolith is an inert material. Okay, thank you.
And before to continue with the following question, I would like just to ask you, how do you deposit your active powder over the monolith? Or, I mean, the question is, do you start from the powder and then do you deposit over the monolith?
Yeah, so yes, we have a special method to coat the catalyst, so that and then we can then try to coat it uniformly. Okay, so our method is actually already published in our paper, so can read the method that we do in preparing the monolith photocatalyst. Okay, thank you. And I continue. There are so many questions in the box, and the next one is from Russia, from Moscow University, and is still for Professor Aishah. And practically, the question is related to the role of carbon in carbon-doped titanium. Very good question. Yeah, we know that TiO2 is a semiconductor. So what is the role of the carbon? So there are two roles for the carbon. We know that for carbon, they have the electrons floating around. So this electrons is very important for the redox reaction. And the other thing is this carbon actually can hinder the recombination of the electron and holes on the photocatalyst. Okay, thank you. Okay, perfect. Okay, so now I have a personal question for Professor Tu. And my question is related to the nature of catalyst to be used for the dry deforming of methane in a plasma condition. You mentioned that the catalyst used contain copper and gold, if I well understood it is correct.
Yes.
So the use of gold is quite surprising to me, because I never used the gold for the dry deforming in thermal conditions.
Yes.
So my question is related to the role of gold in plasma.
Yeah, I mean, this is actually our poster. I mean, try to use gold. But you will see that actually the best performance, was achieved when used, using corp. So actually, we have done some continued work, and we just use like transition metal catalyst, not like a noble catalyst. Yeah.
Okay.
Yeah, I completely understand that, because gold is too expensive.
Yeah, exactly.
Yeah. You are right. Yeah.
Okay.
Most of our process, we use transition metals, normally nickel, cob.
Yeah, exactly. Yeah, nickel is also very active. Yeah. Okay, now I give the opportunity to my colleague to continue with the question and the discussion. Please, Giuseppe.
Okay, thank you, Nadia. I see in the box there is a curiosity for Professor Amin. The program used for visualization of CO2 hydrogenation process.
Right, yeah, it's nice, yeah. So, so we use the Ovito software to visualize that all these atoms.
Okay, thank you. I have another question summarizing also previous points regarding CO2 photoreduction and this potential as key emerging technology. I would like to ask Professor Amin, which are the current issues still limiting the overall efficiency of the process? I mean, is there a catalyst problem in terms of formulation for a proper activation of reactants, or a major problem is constituted by the choice of the reactor and the experimental conditions behind this choice?
Right, very good question. So people use photocatalytic reactors for many purposes. So for example, they have used for wastewater treatment. They have also used for other types like for biomass conversion. So in this case, we have to look at the application. So for like say for this CO2 hydrogenation, so there are also two methods, like you use CO2 in a slurry reactor. Okay, so when you use in a slurry reactor, then the challenge is probably in the how we can have the light intensity, how we can have a strong light intensity, so that we can get a high conversion. So the problem with photo is that the energy, the irradiation energy is we cannot concentrate it good enough or efficiently to the semiconductors, to the photocatalyst for the reaction to occur. Okay, the other challenge is, for example, like the one that I showed just now, when we have the gaseous reaction, we have the CO2 and also we have, like say, maybe methane to react. So both are in the gas phase. So that's where we need a large surface area besides having the light intensity, okay, a strong light intensity. So that's why we have to work with the UV-vis range or also visible range, because this UV is not good enough, it's not strong enough to convert. And of course, when we deal with material, with the photocatalyst, so there are many combinations that we can look at, but the most important thing is how we can make it, how we can come up with a cheap material, a cheap photocatalyst efficiently.
Okay,
thank you.
There is another question for you. Can the recent application of 3D printing in catalysis and reactor engineering find a space in the preparation of a monolith photocatalyst, so to determine a full control of physicochemical properties as well as a reduction of a possible heat or mass diffusion phenomena positively affecting the photocatalyst efficiency and lifetime?
Very good. Yeah, of course. You're giving me the idea. Yes, of course. You know, eventually we'll move on to that, the 3D printing, the monolith, and that for the photo reactor. Yes, wonderful, wonderful idea. So we should go towards that also.
Okay, one last question for both the speakers. Obviously, the escalation of fuel prices and the tendency to reduce carbon footprint validates the importance of such innovative approaches for CO2 utilization, despite a readiness level quite low. So the question is, are you confident that TRL of these technologies can quickly increase, let's say, in a short time, so to be competitive with other CO2 processes? Please, Professor Tu.
Yes, we actually are currently working on that actually to improve our TRL. Yeah, because we find that, I mean, it's quite promising for the plasma technology to be used for like localized or distributed energy storage using renewable energy sources, especially like intermittent energy, because we can switch on, switch off the process very quickly. And also we do not we can do the reactions at room temperature and also ambient pressure to avoid using like a high pressure process. So it's quite promising. So we're currently working on that. I mean, current challenges for plasma-catalysis is still the energy cost for like for example making methanol is still higher compared to like thermal catalysis. But I think we need to do more work actually to improve the the catalyst activities, selectivities to enhance the overall energy efficiencies. Yeah. So I think currently the TR is about like 3-4, but the next step is go to like 5 to 7. So
okay,
yeah,
Professor Amin, what do you think about the maturity and the capability of these technologies?
Yes, I agree with Professor Tu. It's very promising. We are working on the TRL, improving the TRL. So we hope that with this technology, with the improvement, where we understanding of, like say, the simulation work from our mechanism, in fact, from the materials, we can actually improve the TRL and actually try to commercialize this technology, whether it's photo, whether it's plasma, it could be possible. I think for photo, the wastewater treatment is quite a promising method because people have done a lot of work on that, and when it involves just the liquid phase, as I mentioned, it's not that challenging. But if you involve with the gaseous phase for this photo, then it is a little bit challenging.
Okay, thank you. New questions arriving. A question to Professor Tu. Is there a way to modulate the interaction of plasma with intermediates in surface? If yes, what approach do you use? The path for the formation of methanol was simulated? Please.
I mean, this is a very good question. I mean, actually in plasma catalysis, I mean, the interaction between plasma and the catalyst is very important, okay? So we previously have tried a different, for example, packing. So how we put the catalyst in plasma, for example, we can put the catalyst in the whole plasma areas or just put a small amount, and they actually will change the interaction between plasma and also catalyst surface. Because when you mention that you want to modulate like intermediate formation on the surface, this is actually the way that you need to moderate, or to actually understand the interaction between plasma and the catalyst surface, because they will interact each other. So for example, you can use different particle size, and this can also change the interaction between plasma and also catalyst. And the way that we are currently doing, for example, we use water electrode, which can also change the plasma properties and also change the plasma and the catalyst interactions, because they are different. So there are different ways. Also can use, for example, like pulsed plasma power, and you can also change the different interactions. So this is very complicated, but to understand this one, you will need to first you understand the catalyst effect on the plasma, and the second one is how the plasma affects the catalyst. So for the first one, you need to do diagnostics of plasma. For the second one, you need to do like catalyst analysis, characterization. And the best way, of course, if you can do in situ, like a GIFT, it will be much better, but it's very challenging. So in terms of the current, the proposed pathways for the formation of methanol, this is based on the plasma chemical kinetic modelings, integrated with, combined with like optical emission spectroscopy diagnostics and also catalyst characterization. But we also currently working with other groups on the DFT modeling for this kind of process to understand the formation of methanols. I mean, to actually get to the more solid evidence for the proposed the pathways.
Okay, thank you. I see there are other more questions. So Nadia, if you like, you can finalize this moment, this session, please.
Yeah, okay, thank you, Giuseppe. So we have time for the last two, maximum three questions. And there is another one for Professor Amin. As you know, one of the best features of Monolith is a reduction of pressure drop to the bed length. Do you have any idea about this effect? Or do you think that can influence the performance?
Yeah, it's a good question about this pressure drop. Of course, when we have packings, then we will have this pressure drop. So in this case, I would say that since when we work in the lab, we are just using a short monolith. Okay, so the pressure drop issue did not come up. But I understand if you are talking about how to commercialize this. So it's very important that we look at the design of the monolith, because each monolith we have the channel per square inch, so we can see that the channels, is it large or is it small, so we can try to optimize the design of the packing of the monolith when we want to scale up the monolith photoreactor in the future.
Excuse me, which are the dimension of the channels of your monolith?
Which dimension you mean?
Yeah.
For our experiment, what we did, we took a square 6 by 6, and it's about 100 channels per square inch. So
Okay.
yeah.
And did you use metallic monolith, corderite?
Corderite. Yeah, we use corderite.
Okay.
Okay.
And for me, it's just my last question for Professor Tu, and this is a mechanicistic question. I mean, you show that by comparing titania and barium-doped titania, you observed an increase of titanium 3+ in the barium titanate. So this means that you observed an increased oxygen vacancies. My question is, how do you explain the effect in the photocatalytic CO2 splitting? It is due to an effect in the band gap. It is due to the stronger CO2 chemisorption.
Yeah, actually, when we say this is when we say that the UV intention with the photocatalysis, so this is the conventional photocatalysis. But when we say that we use electrons from plasma to activate the photocatalysis, this is actually it's not like a classical photocatalysis. So normally you can use like a photon to activate, for the photocatalyst, but actually in plasma, the UV intensity is really low. We have done the reactions using UV with pure CO2, and nothing can happen. But only when we use plasma with the photocatalyst, we can get the conversion of CO2. So this means actually the UV intensity actually is quite, and the contribution is quite minor in this kind of process. And the electrons, because the plasma can generate electrons with a range of electron energy. So we have some electrons which have higher energy, for example, over like 3 EV, and which can actually activate this kind of photocatalyst. So I think this is the major contributions. But of course, sometimes it could be possible that you can change the band gap or something, because the plasma can be used for the material like synthesis.
So I don't know.
I see there are other more questions, but I wish there will be another opportunity to build another discussion on this topic. So I would like to thank Professor Aishah Amin, Professor Xin Tu for fruitful discussion and insight on CO2 valorization. And from my side, I would like to thank all of you for your kind participation. So Nadia, if you want to close the session, please.
Yeah, me too. I would like to thank both speakers, all people who attended the webinar and asked several questions. And I would like to thank MDPI for having organized such event. And so thank you very much, Charlotte. And I would like to thank Giuseppe Bonura for co-chairing winning such a webinar.
Thank you, Nadia.
Thank you everyone for your time, for joining us. Very interesting presentations. And like Giuseppe said, yes, please, if you ever want to dig further with this, we are very open to the idea. So hope to see you all soon and have a lovely day, everyone.
Okay,
Thank you, everybody.
Bye.
Thank you. Bye. See you on the next meeting.